now we'll try to see how to model the eccentricities in electrical motors. So generally, we do have three types of eccentricities: static, dynamic, and mixed eccentricities. Static eccentricity is where the rotor axis is shifted from the stator axis, and the rotor is rotates about its new axis. And dynamic eccentricity is where the rotor is shifted to the new axis, but the rotor rotates with respect to the stator axis. So mixed eccentricity, so it is a combination of the static and dynamic eccentricity phenomena. So normally we'll start the for the pre-processing stage, we can start the model from the coming from the flux motor. So when we export the model from the flux motor, we need to be ensured that we need to export the full model, because the eccentricity analysis can be done on the full 360 degrees of the 360 degree of the model. So normally in flux, to model the eccentricity, there are two ways. One is with the help of the 6 degrees of freedom macro, so where it can automate your eccentricity operation with respect to the shift of the rotor axis. And the second way is to manually model the eccentricity by editing the lines of the air gap. So in this session, we'll see the how to model the eccentricity with respect to the macro, which will be a more efficient way of modeling the eccentricity. So generally, it will create three parameters. So one is with respect to the x-axis displacement, and one with the y-axis displacement. And if you do have an angular displacement of the rotor, then it will also create the that parameter as well. So we'll try to go with a quick demo now. So we can start the model which we got from the flux motor. That is basically a full model. So once we get into the Flux UI, so we can load the macro here. So this macro will be available in the regular Flux installation. So the macro will be then we have the name with create eccentricity mechanical set. So then you can run the macro here where it asks for the coordinate system and the reference coordinate system, and then you have the what is the rotating speed at that particular working point. And here we are giving the air gap length of this motor is 1 mm. So we are trying to giving the 25% of the static eccentricity. In this case, we are not considering the dynamic eccentricity, so we are giving 0 there. And if you wanted to go with the mixed eccentricity, you can give both of them. Now here we are giving the pole pair number. It is a 8-pole machine, so we can give the pole pair number and you can validate this macro. So as I told, it will create the new mechanical set, that is with respect to the rotor eccentricity. So which is with a type of mechanical set as 6 degrees of freedom. And then it will also create the new coordinate system where the rotor is shifted with respect to this coordinate system. Now the next operation is we need to shift all the rotating parts of the rotor to the new mechanical set what has been created with respect to the macro. So we can see here all the rotating components, and we are changing it to rotor eccentricity new mechanical set. And the air around this rotating component should be compressible, because we do have a variation of the air gap. The air gap is not constant. So we do have the remesh. We need to remesh the air around this rotating part. So that is the reason we are going with a compressible mechanical set, which allows us to remesh the geometry at each step. And later you can delete the existing scenarios and you can solve the model with the new scenario which is created with respect to time. So then we can create a new scenario now. So before doing that, we need to delete the components which are really depending upon the rotor mechanical set. So here we are solving with respect to time now. So then here we are solving the model with respect to one full mechanical rotation due to the eccentricity operation. Then only it will try to extract the forces correctly. So here we do have a 4-pole pair mission. So that is the reason we do have 4 electrical cycles is equal to the 1 mechanical cycle, that is 15 milliseconds, and we do have 1 step for each rotation. That is the reason we do have, it is normally advised to take 1 step for the each rotation. Then it is normally it is required to check the physics before you go to solving to ensure your model is correct, and then you can solve the model. Yeah, once the model is solving, now we can uh, see this eccentricity with respect to the forces. So due to the eccentricity, the forces on the opposite tooth will be not same. So we'll try to create two sensors with respect to the radial component of the eccentricity. So then you can evaluate the sensors. Now you can plot the force components, that is a radial force component on the opposite tooth. So why we chosen the opposite tooth? Because we do have the variation of the air gap. At one position we do have a smaller air gap, that is at this position, and the other side we do have a larger air gap. So when we try to have in one graph, we can see the force is higher when we have a smaller air gap, and the force is small when we do have a larger air gap. So we can also represent this eccentricity operation with another post-processing quantity to compute the force on the rotor and also the stator. So generally when we see the rotor force and stator force, here the rotor force is computed on all the magnetic parts of the rotor, and the stator force is computed on all the magnetic parts of the stator. So we can see it is equal and opposite. So one of the interesting result for the eccentricity operation is where we can have the we can plot the average forces here on the tooth, and we can see that we do have the more magnitude of the forces whenever we do have a lower air gap, and we do have a less magnitude of forces whenever we have a larger air gap. So then I would it is so if further if you wanted to go with NVH simulations, if you wanted to export the forces, then it is recommended to compute the forces with respect to the generalized projective method whenever you have the eccentricity operation, and then you can do the FFT as Simon explained earlier, and then we can export the forces. So to know more about the eccentricities, so we do have already a couple of videos in the YouTube, which you can try to refer them, where we already explained how to manually create the eccentricity modeling in Flux, and we do have another video on rotor eccentricity modeling on the axial flux mission, where we do have axial eccentricity, and we also do have the knowledge based article on the rotor eccentricity modeling. So thank you. That's all from our side.